The goal of this video is to derive what are the properties that a Pareto optimal allocation needs to satisfy. In order to do this, both in the context of the exercise and in future applications like problem sets, we need to derive a couple of results that are going to be extremely useful. So the result states the following. The first one, let alpha be a feasible allocation. Then the following two statements are equivalent. Alpha is Pareto optimal is equivalent to saying that alpha maximizes the sum over I of ui gamma I over all gamma feasible. In other words, saying that an allocation is Pareto optimal when it's feasible is equivalent to saying that it maximizes the sum over all individuals of the utility granted for any possible feasible allocation. Okay? That result is going to be very useful, as you will see in a second. Let me emphasize that as many of the results that we derive in this course, this requires, or it's going to be true only under the assumptions of quasi-linear preferences or utility, and the good M, the amount of M that can be consumed, is unbounded, bounded below. In other words, consumption of M can go negative as much as necessary. This is going to be required. Now, let's see why this result is true. Let me prove it for you. So why? Now, the proof is going to have two parts. To prove that something is equivalent, we can prove that this, the left-hand side implies the right-hand side, and the right-hand side implies the left-hand side. In this case, it's useful to do something that is logically equivalent. On this side, we're going to prove that if alpha is not Pareto optimal, then implies it doesn't maximize the sum of the u's. And in this side, that will prove that if this is not true, this is not true. So therefore, this is necessary for this to be true. And if something not maximizes the sum of the u's, this implies it's not Pareto optimal. In other words, if this is not true, this is not true, which means that this is also necessary for this to be true. And that proves the equivalence. Okay? So let me start with this case. Suppose that alpha is not Pareto optimal. What does this imply? This implies that there exists I with the utility of, this implies that there exists another allocation, there exists feasible beta, remember by the definition of Pareto optimality, that makes one person better off and at least one person worse off. So when we add across subject, there exists a feasible beta at which the sum over all consumers of the utility of I at beta I is greater than the sum of the over all consumers of the utility I at alpha I. Now, why is this true? Remember, let me emphasize and repeat, because if alpha is not Pareto optimal, we can find another beta that makes one consumer strictly better off and nobody worse off. So when we add across consumers, we get this inequality. But clearly, this implies that alpha is not maximizing the sum of the UIs over feasible allocations. So that proves this direction. Let's look about the other one. So suppose that alpha is not maximizing the sum of the UIs. This implies that there exists an allocation beta, feasible beta, for which the sum of the UIs over beta I is greater than the sum of the UIs over alpha I. But then I claim that this implies that there exists a feasible allocation gamma with the sum of the UIs over gamma I, there exists a feasible allocation gamma with the property that UI gamma I is strictly greater than UI alpha I for all I. In other words, I claim that if this is true, then there exists another allocation gamma that makes everybody strictly better off. Which, if this is true, and I have to show it to you in a second, this would imply that alpha is not Pareto optimal because it violates the Pareto improvement test at the allocation gamma. So to conclude the proof, I have to show you how to construct the allocation gamma out of the allocation beta. It's actually quite intuitive. So gamma is given like as follows. In terms of production, we have that every firm produces the same thing at gamma and at beta. So that has not changed. And the same thing is for consumption of good Q for the consumers. That has not changed. The key thing that has changed is the consumption of good M. And in particular, we are going to have that the amount of good M is going to, at allocation gamma for any consumer, is what it got at allocation beta plus the sum of two terms. The first term is the UI of alpha I minus the UI of beta I. In other words, we add or take from what it got of good M at B this number that can be positive or negative, and then we add the sum of UI beta I minus the sum of UI alpha I divided by C. Now notice the following, and this is the important part for the intuition. What we're doing is reshuffling the good M from the allocation beta to the allocation gamma. How do we know that? Because the sum of this term, the sum over I, is equal to 0. That means it's just a reshuffling, just do the addition. Notice one more thing that is critical for the intuition. If we only had this term, if the only reshuffling that we did was this, then what we have is that all I would have, for all I, the utility I at gamma I will be equal to the utility I of alpha I. In other words, what we're doing with the first term is adding or subtracting the good M such that the consumer is equally well off at allocation gamma than allocation alpha. But what is the final part that you need to notice is that this term is positive, is greater than 0. That means that we're starting with a point in which everybody was indifferent and throwing a little bit extra, which implies that at gamma, everybody is strictly better off than at the initial allocation. Don't be overwhelmed by the details. It's actually very simple. What we do is we construct gamma from beta, but not changing Q, but reshuffling the amount of good M in a feasible way to make sure that everybody is strictly better off. Now we get to our second result, which is going to be even more useful in practice. And the result says the following: claim let alpha be a feasible allocation as before. Then we have that the two things are equivalent. Alpha is Pareto optimal, is equivalent to saying that alpha maximizes social surplus at alpha, at gamma, let's say, over all gamma feasible allocations. In other words, Pareto optimality is equivalent to maximization of social surplus over feasible allocations. And as before, let me emphasize that this requires, or this assumes, quasi-linearity of utility and M unbounded below. We're going to use that in the proof. Now, how do we establish this result? How do we know that this is true? Well, we know that alpha Pareto optimal is equivalent to alpha maximizes over gamma feasible the sum of the utilities. We just proved that. But we also know that this is equivalent to maximizing the over feasible allocations social surplus over gamma plus a constant. And see, the constant do not matter for maximization, we have established the result. Now the key question is, how do we know that? This was proven in Unit 4. Now the result that we have proven have two important implications that I want to highlight. So the first implication is that the properties of a Pareto optimal allocation do not depend on the distribution of m's. In other words, if you think about what we just found, is that to characterize a Pareto optimal allocation, we need to solve the maximization over feasible allocations of the social surplus, and social surplus does not depend on who gets what m. So this proves in a very tight way that Pareto optimal is orthogonal to a distribution or equity. These are different concepts. The second thing is that now we get a formula for how to characterize the Pareto optimal allocation, which is how to find Pareto optimal allocations. You have to solve this. Maximize over Q1 of the consumer, so basically how much does every consumer consumes, how much does every firm produces of the social surplus, and I'm going to spell it out here, the sum of I of BI QIC minus the sum of other firms of CJ QJF. Subject to feasibility, which means that the sum of the QIC is equal to the sum of the QJC. Now, strictly speaking, you need to use a Lagrange multiplier to deal with the constraint, but go back to your knowledge of Unit 1. You can simplify this by basically substituting the value of one of the Q's using the equality constraint, plugging it back here, and then solving the maximization problem with respect to that. Okay, I'm very aware that this is a multivariate maximization problem. I'm not going to be asking you to solve them explicitly. I'm actually going to solve it for you and give you some formulas that you can just apply. And this coming in a second. If you take the first order conditions of the maximization problem that I just gave you, you get necessary conditions for Pareto optimality. In other words, these are conditions that any Pareto optimal allocation needs to satisfy. And this can be organized into the following three types that are very useful. So property one is called efficient allocation of production to firms. And what this says is the following is, for any firms, let me call them J, H, and K, with, let's say, QF of J greater than 0, QF of H greater than 0, and QF of K equals 0. In other words, take three firms, any three firms, two of which have a positive production and one of which has zero production. It has to be the case that the marginal cost of firm J at that point is equal to the marginal cost of firm H at that point, and that has to be less than the marginal cost of firm K at its level of production. Okay, so these are properties that the level of production have to satisfy at our Pareto optimal allocation. Second property, which is analogous for consumption, efficient allocation of consumption to firms, to consumers, or efficient allocation of consumption. And it says for any consumers I, J, and K, with the two consumers I and J consumer something positive and consumer K consuming 0, it has to be the case that the marginal benefit for I at what it consumes has to be equal to the marginal benefit for J at what it consumes, and has to be greater than the marginal benefit for K at 0, which is what it gets at the allocation. And finally, it has to be a third property that we're going to call overall production efficiency. And this just says that for any consumer I and firm J with the amount consumed greater than 0 and the amount produced by that firm greater than 0, we need to have that Bi prima of Qiz has to be equal to C prima of J of Qfj. Okay? Think of this as 3 classes of tests that any Pareto optimal allocation needs to satisfy. If they are violated, the allocation is not Pareto optimal. Let me explain the intuition for each of the properties, starting with property 1, efficient allocation of production to firms, that I have rewritten for your convenience here. The basic intuition is that we want to allocate production to firms to minimize the total cost of production. And if this condition that I've written here is violated, then we are not producing what we need to produce at the cheapest possible cost. Let's see why not. So for example, suppose that the condition is violated, so C prima of J of Qfj is greater than C prima of H of Qfh. Then we cannot be producing efficiently, because if we decrease, for example, production in firm J by a tiny bit, so we said we bring this down by an amount dqj down by a marginal amount, and what we do is we increase this by a amount dqj by the same amount. Total production has not changed, but notice what happens to cost. So total production unchanged, but cost changed as follows. We have that total cost, or the sum over cost, or overall cost, change as follows. We have that C prima of J Qf of J dqj, and this is a negative term, plus C prima of H Qfh times dqj, and this is a positive term because this was a negative decrease and this was an increase, and this overall is less than 0 because this term was bigger than this term. So that decreases total cost. In other words, if this condition is not satisfied, we can reshuffle production around on the margin to decrease total cost of production. Now let's see the intuition for why the second property, which is the efficient allocation of consumption, has to hold. So I have, for your convenience, rewritten the condition again, and let's see why. So for example, suppose that we have a situation in which this is violated. Say the derivative or the marginal benefit for consumer I at what it gets is less than the derivative of consumer J for what it gets at an interior allocation. So suppose that is the case. So I claim that we can produce a Pareto improvement. How? What we do is we take a marginal amount of units of Q dq from this guy with the low marginal benefit, and we give it to the guy with the high marginal benefit. So we move things in this direction. And then we also change the M in the other direction by an amount given by dq times the difference in the marginal benefits just by the amount of the marginal benefit of the low guy. Okay? So I'm proposing a trait that defines a new allocation that I claim is Pareto improvement. Why is that? Well, notice the impact on the welfare of person I. We're taking this much out, so its total impact of welfare is minus dq times this, but we're compensating him with exactly the same amount in cash. So person I is indifferent. Now what about person J? It gains dq times this much, and it only loses dq times this much. But since bj prima is greater than bi prima, we have that J is strictly better off, which implies the trade is Pareto improving. In other words, if we violate these conditions, and we can play with different cases, but I hope this gives you the intuition, that means that it's possible to construct a Pareto improvement. Now consider the intuition for the third property called overall production efficiency that, again, I have rewritten for you here for your convenience. Suppose that that is not the case, to see why. So suppose, for example, that BI prime, the marginal benefit of I at this interior allocation consumption level, is greater than the marginal cost of this firm J that is producing a positive amount. Then I claim that this cannot be a Pareto optimal allocation because it's possible to generate a Pareto improvement. How do we generate the Pareto improvement? We get the firm to increase production by DQ and give this marginal amount DQ to the consumer. And we get the consumer to cover the cost of the firm by decreasing DM by minus DQ times CJ prima QCJ. Now, that makes the production of the firm efficient because the extra costs are covered by decreasing the amount of M that the consumer gets, so feasibility is maintained. But notice what happens to the consumer is utility go up, so the change in utility for I is equal to DQ times BI prima of QIC minus DQ CJ prima that QCJ, which is greater than 0. In other words, if the marginal benefit is greater than the marginal cost, we can improve utility in the economy by taking the cost of production from person I and increasing the amount that it gets produced and therefore consumed by person I by a tiny bit. The conditions for or properties for Pareto optimality that we have just derived are necessary conditions. In other words, if an allocation does not satisfy them, that means the allocation is not Pareto optimal. But what about sufficient conditions? Can we find a set of conditions that guarantee that if the allocation satisfies those properties, it is Pareto optimal for sure? Now, finding general sufficient conditions is a difficult problem in general, especially in the presence of semi-fixed cost or fixed cost, but under some conditions that will largely apply to many of the models that we will study, it's easy to find such conditions. And in particular, if we have that the marginal benefit function is greater than 0 and decreasing, and we have that the cost function is so satisfies decreasing returns to scale, then we have that the first order conditions for Pareto optimality are also sufficient. And remember, these first order conditions are the properties 1, 2, and 3 that we have just identified.